The extreme high-performance computing facilities at Livermore allow us to predict very rapidly material properties at the very high fidelities. And these simulations and results then can be used to guide material selections and also optimizations process. So in this way, simulations and modeling can reduce the cost and also reduce the time required for material development. Examples include predicting advanced materials for lithium-ion batteries, supercapacitor, CO2 capture and conversions, hydrogen's production and storage, and also ultra-wide bandgap materials for energy-saving electronic devices.
One area of particular interest for our research at MSD is the simulation of materials at extreme conditions. By leveraging the supercomputers at the lab, we have been able to run some of the largest molecular dynamics simulations, sometimes in excess of 10 billion atoms. We've been able to simulate microscopic phenomena that relies on atomistic descriptions. The chemistry and performance of energetic materials is another area of interest for MSD, where we study the performance and safety of how to handle explosives via computational techniques.
Why would one want to model high explosives on a computer? This question actually has deep historical roots. Some of our earliest understanding of how explosives actually operate, what causes them to detonate, go back to early computer simulations in the 1960s that were performed on Department of Energy computers. Those simulations, which were looking at how material microstructural defects interact with a shock wave, were instrumental in understanding the actual physics of what makes an explosive detonate. The ideal use case of a Livermore weapon product is that it's never used. It is assembled, it sits on a shelf, it acts as a deterrent, and it's disassembled. And across that entire time history, which is many decades, we want no safety surprises and no aging surprises. So computation fills both the understanding how materials age, but also projecting those forecasts forward in time so that we can make some sort of assessment, closely coupled with experiment in most cases, about the longevity of our products.
Here at the lab, we turn to really bridge the scales and trying to develop a multi-scale modeling framework to really understand materials performance. For example, we do a very detailed large-scale atomistic simulations and trying to understand atomic level interactions and how this leads to the desired structural property relationship you want to obtain for the enhanced performance. And then we move to a larger scale of looking into the particle-particle interactions and how you want to manipulate the microstructures to give you the desired performance of the material. And eventually, all this information will be collected and contributes to the device level of design, that how you want to optimize the materials components and its functionality.
The computational research is really important for helping us on the experimental side for a couple of reasons. So one is that a lot of times when we make the batteries and we test them, we might get a certain performance. Maybe it's not performing so well, but we don't really know why. And there are a million different reasons why it could be performing that way, but we can't really test all of those experimentally. So it's really helpful to have the modeling where they can look at things on a smaller scale, on the atomic scale, and really understand what's going on. If we know why our batteries are performing that way, then we can try and develop new solutions to make them perform better.
So we're really excited about the use of quantum computing in the future for materials research because it will allow us to compute chemistry and materials properties at an unprecedented accuracy and with system sizes that really are not possible with classical computing. We're also engaging currently in using our material science expertise to advance the state-of-the-art enabling technologies for quantum computing itself. For example, we're investigating how to optimize fabrication and material selection for a range of quantum bit technologies, including superconducting, semiconducting, and ion trap qubits. so that we expect our work will advance the state of quantum computing so that we in the future can use it back to impact our material science in a really nice closed cycle.
What excites me the most about being in Lawrence Livermore National Lab is people. We are surrounded by thousands of excellent, energetic researchers with a very diverse background from physics, chemistry, material science to computer science. And that wide range of expertise makes Livermore become one of the ideal places for teamwork, and you cannot get bored because there are always opportunities, new ideas, new directions that pop up almost every day.